All right, so the paper I'm presenting today is called Extraction of Fast Changes in the Structure of a Disordered Ensemble of Photoexcited Biomolecules. It came out in 2013 by Poon, Schmidt, and Saldin from UW Milwaukee. Hi, guys. It came out in Advances in Condensed Matter Physics. So this paper is concerned with a time-resolved experiment that isn't studied as much as, say, the crystal time-resolved experiment, which has been many simulations on. There's been a lot of experimental work on it, and the single molecule, which is sort of the goal of the field, right, to move to single molecules eventually. We're not at single molecules yet, so the question is, what can we do with solutions, which is where we're at now. And so typically at the LCLS, you will have this liquid jet of protein in solution traveling that's jetted out of some nozzle from upstream here. And if it's photoexcitable, there will be a laser here which excites the protein to some excited state, and it comes through the XFEL beam during some reaction intermediate, and you have some scattering or some diffraction to the detector. Now, this is good in some ways and bad in some, which I'll get to in a second, but eventually we'd like to have either a single molecule by itself, with most of the solvation water stripped off into the XFEL beam and detected. That single molecule diffraction is what people really want to get to, but we're not there right now. Currently, the best we can do at XFEL as far as molecule presentation is something in this range where we have lots of proteins solvated, and for sort of a minimum solution volume, which is something on this magnitude, optimal concentration of proteins, which you want to have super high in order to limit water scattering versus protein scattering, may contain up to something along the lines of 10,000 molecules of PYP, for instance, which is fairly small. If it's bigger, there will clearly be less of them, but still nowhere near, say, 1, which we want to get to eventually. But in this case, which is non-ideal for a few reasons, can we still gather really good structural information? And so this is what this paper is trying to address: is how good can we do with the current experimental design, and in what ways can we get good structural information out of this design setup at the LCLS. So there are some advantages to having this jet as opposed to crystals or single molecules. Advantages of this versus SACs, for instance, the XFEL basically allows for a frozen-in-time molecule snapshot. So the XFEL is so fast, femtosecond speed, that none of the molecules are going to be able to rotate around, so you don't have to solve for each individual molecule rotating. You can get physiologically relevant temperatures, which is better than, say, a synchrotron or some cold SACs, where you have to really cool down the sample to slow all the motions. You can hit things as they move at physiologically relevant temperatures, so you can get really, really good kinetics out of it. Proteins are free in solution uninhibited by crystal lattice, so there aren't motions that are unallowed based on crystal packing. So these guys should behave better than they behave in almost all other structural interactions as far as understanding the kinetics of the system. Disadvantages: no crystal means you have random orientations. You have lots of protein in the beam that isn't ordered in any specific way. The diffraction is an average over multiple molecules in the same shot, which means that you have a bunch of guys in a bunch of different orientations, and it's worse than crystals, which is a bunch of different orientations. At least within the crystal, they're all the same. Diffraction over multiple molecules in the same shot that are all disjointed is a disadvantage, clearly. And resolution is limited by the lack of crystal, because you don't have as much diffracting power, because you have a single molecule versus a bunch of molecules together to add to your diffracting power. So the question is, how can we do this well? In this situation, what's the best case for getting really good structural data out? And so the model for this paper uses PYP, which is photoactive yellow protein. It's a model-like responsive protein. It's a really good model because it's simple as far as photoexcitation is concerned. There are 2 main moving parts. You have the chromophore that moves here and sort of swings out in a 180-degree fashion down to here, and this arginine, which gets out of the way and turns 77 degrees this way. And these 2 parts, while the rest of the molecule remains stable, and these 2 parts are what are allowed to move. And it's really important to understand that in this case, that everything else is remaining stable. Because if the protein overall is molten, it's really, really hard, because you don't have a good search model, to understand what's happening here. So the fact that all of this is stable really plays into your favor. Here we see the density and structural changes considered in this model. So this is the dark structure shown here, with the density, with green being the photoexcited density and red being the dark. So the dark goes away and becomes this, and so you can, as you can see here, everybody's sort of the same, and the difference is really in this pocket. The chromophore moves from this position to this position here, going from the red to the green, and the arginine swings out from this red to the green. And as you can see here, everything else is pretty stable. There's no real density differences at all. And this really helps because it allows us to change these two in search rather than changing the whole thing in searching, which, you know, in factor of n complexity is really a bad case for this. So the fact that we only have n equals 2 really helps the search model, which I'll get into in a second. So how do we do this just in general? How do we calculate structural information from disordered ensembles? And so the answer is you use an angular correlation function. This angular correlation function here is between the intensities of two resolution rings averaged over a set of diffraction patterns. Right, so this DP shows that it's averaged over a set of diffraction patterns. You have two different intensities of different resolution rings. And it turns out that because you assume that there's no preferred orientation between molecule beam detector, that this initial chosen phi doesn't matter, just the delta phi matters. And if there's complete transitional disorder, which again, if we're in a jet, we assume is a good assumption to make, it becomes this, based on spherical harmonics, and where theta of the scattering angle becomes this, and kappa is the wave number of incident radiation. So in this expression, you can solve for this B value here. It becomes the sum of ILMQ and this other ILMQ prime. And we can find the B by inverting this equation here, but finding the individual I in I star is problematic, especially when you have a good search model. This can be overcome if you have a known symmetry. So with viruses, it's been worked out where you have an icosahedral or helical virus. You can get this back, and this paper shows that you should be able to get it back with a known search model, which you can vary off of a protein. So the design for model calculation is they basically ran test cases where they calculate the rotation of the chromophore theta and arginine 52 chi3 by sampling every 5 degrees. So they sort of walked both of them around, and they started from the dark structure, and then they took structure factors for each 5-degree iteration, which got them to this A structure factor value. And this allows for calculations of the test case to get IQ. And so then from IQ you get B, you get the B factor for each test case. So they have 5 degrees of 180, every 5 degrees for 180 degrees they sampled theta, and for 5 degrees for 77 degrees they sampled, well actually for the whole 360 both directions it turns out. But so they did 360 5 degrees for theta and 360 5 degrees for chi3, and then calculated structure factors for each case, and then got the I's for each of those, and then generated this trial model here, and compared it to the photoexcited density converted to this B factor here. And so this comparison between the test and the photoexcited structure yields this R factor here, which they converted into a 2D contour map, which I'm showing in the next slide. And so if you remember earlier that the theta from the dark to photoexcited was 180 degrees, and the chi3 from dark to photoexcited was 77 degrees. And the R minimum is right in this hole right here, because this is 180 and this is 77. And this R minimum, which is the closest agreement, is right in the range where you would expect to find the two things move to. So basically, this agrees because this whole contour map is set up in agreement with the dark state. So you would expect to see everybody moved over here, and this is highly unfavored because you have the chromophore and the arginine both swinging back up into steric blockers. And so this R is heavily favored. And so you can sort of see how you could get a understanding of where you go just by simulating testing. So you have some B factor here that you get from the scattering experiment, the diffraction experiment. Well, it's a trial because you have a known starting point, and if you know what things move, but not necessarily where they move to. You can figure out a trial that you can get to match your model, which gives you something like this. This paper was then followed up by simulations on time-resolved structure determination of uncrystallized biomolecules in the presence of shot noise. So they designed the molecule on the model, not the molecule, the model in the previous paper. Here they go through and show that the model works with noisy data from simulations where they simulated diffraction experiments on the XFEL by Pandey, Schmidt, Schwander, and Saldin, also from UW Milwaukee. Hi, guys. This was published in Structural Dynamics in March of this year. So they simulated diffraction patterns of PYP at 5 angstrom resolution with 1 particle in the shot in this column, 10 particles in this column, and 25 particles in this column. And so these are individual shots that will then be averaged together to create the real space correlations. And well, to create the model, then you get the real space correlations out of that. And so 3 photons per Shannon pixel is basically what's achievable at XFEL now, roughly. And so with 1 particle in the shot, you can see something, but there's not a whole lot of information there. But if you make a factor of 10 improvement in scattering power, you get a really nice diffraction pattern. And the more particles you have, the less diffracting power you actually need in order to get something that has a whole lot more information in it. But if you get to 30, everything sort of catches up and becomes even. And so these are the difference densities from the dark state PDB structures and simulated diffraction patterns. So these red and green difference density blobs here correspond to these guys that they took and made these out of and sort of worked back to the light absorbed, the dark structure. So these are the dark straight PDB versus these that are simulated light diffraction patterns. And these are the maximum correlation coefficient for each one. And you can see here that with the 1 particle per diffraction pattern in the low photons per Shannon pixel, you don't see much information here. You can sort of see this the chromophore going away from the initial dark position, but you don't really see it arrive here. But the more particles you have in the shot, the better off you are, which is a theme we see running through most of these XFEL experiments. The more particles you have, the better, and also the more shots you have, the better, of course. But if you increase the scattering power, the diffracting power of an individual particle, you get to the point where the one particle equilibrates with the others and becomes as good as, if not in some cases better, than multiple particles a shot. Of course, this simulation doesn't take into account solvent scattering, which would definitely cloud this image some, but it is definitely a proof of principle that even with noisy shot-to-shot variation in your scattering data, you can get out these difference densities, which are actually quite pretty. And the real space correlation coefficient on the y-axis here is a function of the photons per Shannon pixel and particles per diffraction picture, which you can see sort of here. You can see that in all of these images, that's how this graph is going to go. The real space coefficient goes up, and it goes up much faster with multiple particles in the diffraction picture. But after you hit a certain scattering power, diffraction power, one particle becomes better as you get less and less noise, right? And so up here you have sort of maybe it would be best to get to single particle diffraction, if you could get no noise. But as long as we're down in this area as far as what's feasible at the XFEL, more and more particles are going to be needed in the shot. Which the more particles in the shot, you're also going to be limiting solvent scattering, which is also a good thing. But you can tell as the scattering power gets higher, the one particle does catch up as far as real space correlation coefficient. So conclusions for this: for some systems, it may be possible to determine dynamic structural changes in solution, but only if the motions are sufficiently simple, right? Because PYP is a really simple system. There are 2 things moving in a much larger molecule, and you have a really good search model to use, and you only have to rotate 2 bonds in order to search the space. But if you have something that's molten, right, if you have something that goes, a large conformational change where you have, whole domains moving, it really becomes tricky, and it hasn't been shown for that yet, but maybe one day. And as brilliance and scattering power increase, the number of particles per diffraction pattern decrease, allowing less concentrated Did I write that wrong? No. As brilliance and scattering power increase, the number of particles per diffraction pattern required decreases, allowing less concentrated protein solutions in the future. So you have more efficient use of protein, possibly. And prior knowledge of steady states is vital to the success of this method, right? Because if you have something that you don't know exactly what the dark state looks like, it's going to be really, really hard to study the excited state. And so the next steps for this path is to collect data corresponding to simulation at LCLS to make sure that even with the solvent scattering and uglier data than simulation, it does still work, and to adapt model more and more complicated systems, introducing more variables, right? So you could think that maybe they could adapt this to having something where you're not going to have as high resolution data, but you could have something where you could see sort of domains folding in and out with less data points, where you won't see C alphas and you probably won't see a fold, but you can see sort of the glob of protein moving in and out if the rest of the protein is big enough and stationary. And to continue to revisit as injected volumes get smaller and X-ray lasers get brighter, right? Because as long as the field is moving forward, we're going to have a whole lot more of this sort of situation before we actually get a single molecule in all likelihood, right? As injected volumes keep getting thinner and thinner and smaller, and X-ray lasers get brighter, this will become a much more feasible technique. And I think that's all I have. Does anybody have any questions?